In this video, we'll start talking about the idea of limits involving infinity. We've dealt with limits quite a bit at this point, but all of them have really only been limits that involve actual numbers, right? Limit as x goes to c, or the limit equaling some number c, all that we've done so far. But now I want to think about limits that involve infinity. And there's two main kinds of these limits here. There's limits where we're taking the value x out to infinity, so something like limit as x goes to infinity of some function f equaling some number L. And these are the nicer one of the two, right? We're just taking x really, really big, really far away, limit as x gets really, really far away. That's what we're looking at here. There's the second case where we have the limit as x approaches some number c equaling infinity. And as of now, I will put quotes around this because it's not really equaling infinity. This is sort of a notation we use to talk about a certain specific type of behavior of limits. Of the two, the first are nicer, and we'll discuss sort of what I mean by nicer. It usually means that it obeys more of our nice properties of limits, whereas 2 really doesn't. Let's look into the first of these. These are limit as x goes to plus or minus infinity. So what do we mean by this idea? So we say that limit as x goes to plus infinity of f of x equals L. And the idea here is we want to look at x when it gets really, really big, or as x gets bigger and bigger and bigger, what's happening to f? And we're looking at sort of long-term behavior of f, what happens really far away. How is f behaving for x really big? So to relate this to our normal idea, we want to say if f of x gets really close to L as x gets close to infinity. But what does that mean? Well, it means that f of x minus L is small whenever x is large and positive. As a side note here, in terms of epsilons and deltas, the idea would be f of x minus L is less than epsilon whenever x is bigger than some capital M, and I can take my tolerance here is how big is M as opposed to how small is delta. But if you have not seen that, you can ignore that point there. I'm thinking as x gets really large and positive, this needs to be small to say this limit goes to L. And similarly, we use limit x goes to minus infinity, f of x equals L if absolute value of x minus L is small for x large and negative. So going off way, way to the left side of the number line, way off to minus infinity. It might be easy to think about this in terms of some examples. So what happens to the function e to the x as x goes to infinity? Well, as x goes to infinity, e to the x keeps getting bigger and bigger and bigger. So this does not approach a number, so this does not exist. Or as we'll see later, we can actually say this equals infinity. And the notation we'll talk about later for that target limit. What about as x goes to minus infinity? As x goes to minus infinity, e to the x is going to 0, right? As you go further and further to the left, that graph just keeps approaching closer and closer to the x-axis forever and ever. So this limit here is 0. What about sine of x? Well, in both cases, sine of x keeps oscillating up and down forever. So there's never any single number that it approaches as x goes to infinity. It's not like it's pinching in or expanding out anywhere. So these both do not exist. Now what about x to the n? This gets a little trickier based on what n is doing. As x goes to infinity, if n is positive, that's a positive power. So that's going up to plus infinity as long as n is bigger than 0. So we'll put in a bracket here. This ends up being at infinity if n is greater than 0. It's 1 if n equals 0 because it's just 1 all the time. But if n is negative, 1 over x to the n is going to 0. 1 over x to the n, if x to the n is getting really, really big, this is going to collapse to 0. 1 over x, graph of 1 over x approaches 0 as x goes to infinity. For x going to minus infinity, the idea is similar, but it's a little more complicated. We have positive infinity if n greater than 0 and even. As for even powers, that graph will go up as it goes towards the left. It's minus infinity if n greater than 0 and odd, because for odd powers, you'll keep your sign and go down. And then, again, it's 0 for n less than 0, because again, we're taking 1 over a bigger and bigger number. Whether it's positive or negative, I don't care. It's still going to go to 0. Now, the big benefit of all of this is that assuming that limits exist, so this limit equaling a number still exists in the normal sense of a limit existing. So if I have limit x goes to infinity of f of x equals L, this limit exists, which means all of our limit laws still apply in this context. We can add, subtract, multiply, divide, all of these things work out great, provided these numbers equal L or some number. When limits start equaling infinity, that's when this whole process breaks down. But for limits equaling a number, this all works, these limits still exist, and I can apply my limit laws to that. The main way you'll see this appearing is in something like this context here. So we have here a rational function. Polynomial top, polynomial bottom, limit as x goes to infinity. Now in this form, I can't really do too much here. Because the top's going to infinity, this limit goes to infinity but does not exist. So I can't just sort of split top bottom and call it a day. What I can do though is I can find whatever is the highest power that I see and divide through by that power. So I can take this and I can multiply top and bottom by 1 over x to the fourth. This doesn't change the expression, I'm just rewriting it in a form that's going to be easier to use. If I do that, I will see limit x goes to infinity, 3x squared divided by x to the fourth is 3x to the minus 2 plus 2x to the minus 3 minus x to the minus 4 divided by 5 survives by itself because fourth and fourth, plus x to the minus 2 minus 2x to the minus 3 plus x to the minus 4. And I want to push the limit through. I'm allowed to do it now because what happens? Each of these terms now go to numbers and they all exist because as I take x to infinity, this goes to 0, this goes to 0, this goes to 0, so the whole top goes to 0, so that's well defined. On the bottom, goes to 0, goes to 0, goes to 0, stays at 5, so I can now push this limit through to the top and bottom into each term. And if I do that, I will get 0 plus 0 minus 0 over 5 plus 0 minus 0 plus 0, or 0 over 5, which is 0. Therefore, this original limit equals 0. To put this more into context, this idea is the same thing as finding horizontal asymptotes. A horizontal asymptote is really what's the function doing as the input goes to infinity. So if limit x goes to infinity of f of x equals L, then the graph of f has a horizontal asymptote at L. With that context, this result probably doesn't surprise you, because in previous classes you probably looked at these sorts of functions and found asymptotes based on the powers of the leading terms on these expressions. If the bottom has a higher power, then it has an asymptote at 0. If the top has a higher power, it goes off to infinity, doesn't have an asymptote. And if they are the same, you get the ratio of these coefficients. This exact process here is how you determine that out explicitly using limits and using calculus. This exact same process of dividing by the highest power and simplifying out works for all rational functions. You can do the same process every time to get to the answer that you want for this situation. So that's the idea of limits as x goes to infinity and how that ties into the idea of horizontal asymptotes. They're really the same thing. The horizontal asymptote of a function is its limit as x goes to infinity or minus infinity, and we can find them for rational functions by figuring the highest power that's present, divide through by it, and then see what we get out of that simplification as the limit goes to infinity for those functions.